So hello, I'm back. Okay, and this is our third piece. Hopefully it will be relatively brief. We're going to solve some equations that instead of having exponential terms in them, they'll have log terms in them. So what if we've got, for instance, something like this, log base 2 of x is equal to 7. Okay, so notice we've got a log term here and not an exponent, right? Okay, so when we're solving equations with logs in them, there are basically two approaches or two methods. Okay, method one, you're going to use if there is a log term or terms only on one side of the equation. So this is method one. If there's a log term or terms maybe on one side of the equation. So that's what we're seeing here. We've got log base 2 of x over here. It's supposed to be a 2. And then only a 7 over there. So in this case, the method, the thing that we're going to do is we use our basically the definition of definition of a logarithm to turn this into its equivalent logarithmic expression. Equivalent exponential expression. So here's the thing. Turn log equation into its equivalent exponential equation. Okay, so that means, using my red here, I'm going to take this 2. If, 2 to the 7 is equal to x, right? So this goes here, and that goes to there, right? So we would say x, or rather we'll put it like this, 2 to the 7 power is equal to x, or x is equal to 2 to the 7, right? Well, what's 2 to the 7th power? According to Mr. Calculator, 2 exponent 7, boom, that's 128. So there's our answer, 128. Okay? Or let's say, so that's going to be example 1 for us. Let's say it was something like this, example 2. Let's say log base 3 of x was equal to, 5.7. Well, that's cool. Again, turning into its equivalent exponential expression, x is equal to 3 to the 5.7. And again, Mr. Calculator will do that. 3 exponent, I just type in 5.7, calculator doesn't care. And I'm getting 524.3. Can you see that? 524.3. Rounded off to the tenths place, right? So we could have something with more steps on the inside. So example 3, so how about log base 3 of x plus 5, right, is equal to 6, right? Now, notice this x plus 5 is on the inside of the logarithm. We can't just subtract 5 because that's not 5. That's log x plus 5. We've got to cancel. We've got to work from the outside in like we did with exponents. So we've got to get rid of the log term first. And the way we do that for these type of problems where there's only a log over here is we turn it into its exponent, right? 3 to the 6th power has to be equal to x plus 5, right? So I'll write it with the x plus 5 first. X plus 5 is equal to 3 to the 6th power, right? And then to isolate the x, we simply subtract 5 from both sides. x is equal to 3 to the 6 minus 5. And 3 exponent 6 minus 5. Okay, that's 3. That's 729 minus 5. That's equal to 724. And these are going to be our answers, right? Okay, so see how that works? Now, okay, let me try some slightly more complicated ones here. All right, what if we've got, so this will be example 4. Okay, what if we've got two log terms? What if it says, oh, log of x minus log of 7 is equal to 1, let's say. Oh dear, look, there are two different log terms on the other side. Well, if this were, say, a more conventional equation, say x minus 7x is equal to 1, what would we do? We'd combine like terms here and get negative 6x is equal to 1, and then we'd go ahead and we divide by negative 6, right? Well, over here, we've got to do the same thing. We've got to combine like terms. We've got two log terms. Now, how do we combine like terms? Well, we use the rules of logarithms. Now we're going to compress using our compression technique that we learned before. Subtraction on the outside is division on the inside. So this compresses to log of, and that's log base 10, of x divided by 7 is equal to 1, right? And this is log base 10 there, right? Subtraction on the outside, division on the inside. Now, we change this whole thing back into its equivalent exponent. 10 to the first power must be equal to whatever x plus 7 is. So x plus 7 is equal to 10 to the first power. I'm sorry, x divided by 7 equals 10 to the first power. That's x divided by 7 is equal to 10, or x is equal to 70. Okay? And you can check your work there, by the way, just for yucks. We didn't do it on the last one, but, you know, log of 70 minus log of 7 is supposed to be equal to 1, right? Well, let's try that on Mr. Calculator here. Log 70 minus log 7. Yep. See there? 1. Okay, so that's just a check. Okay, so that's how that goes. Okay. Or we could have, say, something like, here's example 5, log of x plus log of 4 is equal to 1, right? So now we see, oh look, addition on the outside, we've got to combine like terms of the logarithms here. So the way we do, we don't just add these. Keep in mind, up here, this isn't log 1 minus log 7 and somehow work out to be log 7 or something here. And we're not just going to add this and get, I don't know, x plus 4 on the inside. Okay, this doesn't become x minus 7 on the inside because logs don't combine that way. This doesn't become x plus 4 on the inside. Logs don't combine that way. Addition on the outside, multiplication on the inside, just like exponents. So this becomes log of x times 4 is equal to 1, or log of 4x is equal to 1. And again, that was log base 10 here because I didn't bother writing it. Okay, if you don't see a base, just assume it's 10. Okay, so now this is, oh look, we turned it into its exponent here, just like that. 10 to the x, oopsie, it's all right, 4x is equal to 10 to the first power. 4x is equal to 10. X is equal to 10 divided by 4, which is 2.5. Okay? So those are some log equations there which you can do. Okay? Which you can do on your own. Now, let's try this one. Let's try one more to show you a weird effect that you see sometimes with log equations. Okay, and I want to remind you of this little factoid right here. If I try to log a negative number, remember, if you do on your calculator log -3, it gives you an error, right? And the reason is that the logs, remember the domain for logarithms, the number on the inside has to be positive. It's got to be greater than 0. So if we try to substitute a negative in there, it's undefined. So how does that affect us now? Well, let's say we're trying to solve this equation here, log x plus log x plus 9 is equal to 1. Okay, we're going to combine the log terms. Addition on the outside is multiplication on the inside. So this combines to one single log base 10, because it's the common log, x times x plus 9 is equal to 1, right? X times x plus 9. X times x plus 9 on the inside. That gives us log base 10 of x squared plus 9x. That equals to 1, right? Okay, now that we've got one single log term, we've combined the log terms, right? So now we're going to change this into its equivalent exponent. 10 to the first power must be equal to x squared plus 9x. So x squared plus 9x, 10 to the first power is still 10, right? So now, that's a quadratic equation. It's okay. We're going to solve it. Subtract 10 from both sides. Not a hard one to solve, luckily. We're going to zero both sides, right? Get 0 on one side. I see that, this one factors into x plus 10 times x minus 1, right? That's x plus 10 is equal to 0, x minus 1 is equal to 0, so we get -10 and +1 theoretically are solutions, right? However, here's the problem. Do you see that we put this -10, if we put it up here, we'd get log -10, which is undefined, right? So it turns out that you got to watch out for this with log equations, is that if we get a number that a solution that when we substitute it in for x anywhere, if it makes the entire inside negative, we discard it because it's undefined. It's what we call an example of an extraneous solution. So we discard that one, and the only solution is x equals 1. Yeah? Okay, so which one was that one? I kind of lost count. Okay, that was example 6. Okay, so that's one of our approaches to solving log equations, all right, is if there's a log just on one side. Okay, now, we'll do a couple of these. Here's another example. What if we've got something like log x plus 3 plus log 6, and look, I'm going to put a log expression on the other side. Now these, in a way, are even simpler, because since we've got logs on both sides, and we're only going to have equations where the log bases are the same. So all of these, you know what, I'm going to make these log base 3, because we haven't done that lately. So log base 3 there. Okay, so now we combine like terms, and that becomes a multiplication, right? So this is log base 3 here. inside of 6 times x plus 3, this times that, is equal to log 3 of 5 on the other side. Well, the thing is notice that the log bases are the same. So if the log bases are the same, the interiors of the logs are the same. And so the log terms, log base 3, in effect just cancels out. And we've got 6 times x plus 3 over here is equal to 5. So this is going to be method 2, right? And this is logs on both sides, right? Combine terms. What do we do? Well, combine terms if necessary. And so this is number 1, and then number 2, cancel the logs, leaving what's rest. So this is method 2, that if you've got an equation of the log on both sides, they combine, they're both log 3, so the interiors must be the same. So this one was, I guess this was example 6. Okay, so example 7. Okay, this is, let's try this one, log base 7 of 2x minus log base 7 of 7 is equal to log base 3, or log base 7, sorry, log base 7 of 8. Okay, so now we combine these. Subtraction on the outside, division on the inside. So this becomes log base 7 of 2x over 7 is equal to log base 7 of 8. Well, again, oh look, they're both log base 7. If the logs are this, if the bases are the same, the interiors have to be the same. So in effect, the logs cancel out. And we've now got 2x minus 7 is equal to 8. Multiply by 7, divide by 2, so that's 2x is equal to 56. Divide by 2, x is equal to 28. Oh, look, 28, we put it inside here. That doesn't make that negative. 5 didn't make anything negative up here, so those are both legal solutions, right? Oh, and wow, I didn't even finish solving that top one, did I? Interesting. 6x plus 18 is equal to 5. 6x is equal to negative 13. X is equal to negative 13 over 6. Okay? Should have done that one. Sorry. Okay. Silly. That's negative, and you're thinking, oh, we can't have a negative answer. But we can, because if we put negative 13 in for x up here, so log of, I'm going to do this bit here. So we try substituting, because we're nervous about it, we try substituting the negative 13 over 6 up there. Negative 13 over 6 plus 3, as it happens, works out to be 2/5, which is positive. So negative 13 over 6, even though it's negative, that's still a legal solution because it doesn't make the inside of the negative solution. Inside of the logarithm negative. Sorry about the backtrack there. I hope that wasn't too confusing. Okay, but this is the basic idea. You just got to check for extraneous roots. Okay, so that was method 2. Now what I want to do now at this point is I'm going to give some log ones for you guys to try out, some of these log equations to solve. Okay, and I'm going to change this sheet here. I'm going to write about 4 or 5 over here, right, for you to try out, and then there'll be more on the classwork for you to try out. So why don't you go ahead, let's try these. How about log base 6 of 10 minus log base 6 of 2x is equal to 1. So we're try these. Okay, so these are ones where there's a log on only one side. So how about let's try another one here. So this is number 1, number 2, log base 8 of 6 minus log base 8 of negative x is equal to 2, right? Try that one out. Okay, and then I'm going to leave some more space here. Number 3, let's try one with a log on both sides. Log base 6 of negative 4x plus 4 is equal to log base 6 of 4x positive 4x plus 4. Solve that one. And then number 4, how about log base 9 of 7 plus log base 9 of x plus 1 is equal to log base 9, so log base 9 of 4. So try those out. Okay, put the video on pause, try those out, and I'll be right back with the solutions for them. Okay, I'm back. Okay, so this combines. There's a log on one side, so we're going to use our log on only one side method, but we have to combine the log terms first. Subtracting on the outside is division on the inside. So I've got log base 6 of 10 over 2x is equal to 1, right? Subtraction on the outside, division on the inside. Now we change this to an exponent. 6 to the first power is equal to that bit right there. So 10 over 2x is equal to 6 to the first power, which is 6, right? Multiply both sides by 2x, and I'm squeezing here. That's 6 times 2 is 12x is equal to 10. Divide both sides by 12. X is 10 divided by 12, which is, 10 divided by 12. That is 5/6. Good. So that's what we did there. This one here, again, we're going to combine through division, right? So this is going to be log base 8 of 6 over negative x is equal to 2, right? So again, 8 to the 2 is equal to whatever is over there. So this is 6 over negative x is 8 to the second power, which is, of course, 64. So going sideways here, that's 6 over negative x is equal to 64. Multiply both sides by negative x to spring it out of the denominator, right? And that gives us 6 is equal to negative 64x, right? Divide both sides by negative 64. X is equal to whatever negative 6 divided by 64 is. And that's our answer. Okay? This has got a log on both sides. Hopefully you didn't have to think too hard about this. We've already only got one log here and one log there. They're both log 6, so they both cancel because the interiors have to be equal if the bases are the same. So that becomes 4x plus 4 is equal to negative 4x plus 4 is equal to positive 4x plus 4, right? We add 4x to both sides, right? So that's 8x plus 4 is equal to 4. Subtract 4 from both sides. 8x is equal to 0, or x is equal to 0. So that's our solution there. And you're thinking, wait, a logarithm can, is 0 okay? Yeah, we put 0 back in here, and we get actually log 6 of 4 on both sides. Okay? This one here, we're going to combine through multiplication first, because we got to combine those terms. So this is going to be log 9 of whatever, if we multiply those together, that's 7x plus 7 is equal to log 9 of 4. Again, now we've just got a log on each side. They cancel. 7x plus 7 is equal to 4. We subtract 7. That's negative 3, right? We divide by 7. We get x is equal to negative 3 over 7, right? And you think, oh, wait, that could be bad because that's negative. So we put this up here, and we think, well, that's not going to be negative. That's not going to be negative. So we try log of negative 3 over 7 plus 1, which works out to be log of 4 over 7. And that's positive. So, yep, that's a legal solution. The solution is only illegal. It's only extraneous if it makes the inside of one of these terms negative, which is undefined for logarithms. Okay, good. So that's enough. So a little bit later on, I'm going to be posting your classwork and your homework. But